finally, I'm switching away from filtration. You may have gotten the impression that I could have talked about filtration forever, and that's probably true. Because to be completely fair, we still haven't delved into nearly all of the details that go into designing one of those stacked rapid sand filters. But we got to call it quits at some point. So today, I want to talk about something that might just sound totally boring, but I want to assure you this is not. Inlet and outlet manifolds, so pipes that have maybe multiple holes in them that we use to get water into a tank or out of a tank. Obviously, this is happening inside the clarifier, but it's also happening inside the filter. And we want to think about how does that work? And the reason that I really wanted to cover this is because problems with manifold design and more generally in getting the water to do what you want it to do are very commonplace. It is very common in water treatment plants for the water not to do what the designer hoped it would do. And there are still clarifiers, sedimentation tanks being built that don't work as intended because the water doesn't do what the designer was hoping. And certainly there are filter failures because of lack of a good flow distribution. So I want to introduce you to why that's an issue and kind of what makes it complicated and what some of the really big ideas are. I'm going to try to avoid going through all the equations because I feel like that doesn't connect very well, but there is a chapter in the textbook that you can use for resources if, as you go out in your career, if you run into this issue of how do you get uniform flow distribution between multiple paths, come to the textbook. There's at least some good guidance there. And oh goodness, and we end with in which change in kinetic energy becomes significant. Thanks to the writer of Winnie the Pooh, because kinetic energy shows up in a surprising way in this problem, and hopefully we'll enter that today. So some more context. Remember Agalteca? I'll show you some pictures to remind you of that problem. And just this insight that water treatment plants commonly have processes where flow divides into many, many parallel paths, and I'll show you where that's happening in an agua clara plant. And it is very easy to have poor performance because the flow isn't dividing the way you might have hoped it would. So this is a reminder of Agalteca. Remember we built this plant, this was the clarifier, and we had a problem with flocks coming up at the end of the clarifier. And it turned out that the problem was related to water having a velocity component that we weren't expecting, and that causing a mean flow of water towards the end of the clarifier. I want to point out that I just, on Monday, I spoke with one of my former students who's working at the Cornell University water filtration plant. And over spring break, Cornell water treatment plant shuts half of itself down, and they operate longer hours to make sure they can still deliver enough water, but demand is down because the students are gone. And they have a large horizontal flow sedimentation tank, and it accumulates sludge over the course of 6 months. And so my former student was in there helping to clean out that sedimentation tank, and he showed me some photos, and he showed me that in that sedimentation tank, the outlet used to be right at the end of this horizontal tank. And then at some point, there was a retrofit and it was moved back about, I don't know, maybe 10 feet or something. And so it's no longer at the end of the tank. Now, I don't know for sure why that happened, but I have a very good guess. And my good guess is that they discovered that all the flocks were coming up at the end of the tank. because the water is flowing horizontally down through this tank, and it all comes up at the very end, and it lifts a bunch of flocks up from the bottom right at that point. And so the end of a sedimentation tank, a horizontal sedimentation tank, is a bad place to collect what you thought was going to be clarified water. So this is just another example of water not doing what you might have first expected. And then, okay, how many places in a plant do we have multiple paths where the water can go? And we're hoping that it divides equally between those paths. So there are many places, and I'll show you some of them. And you can think about, why is this important? Like, if all of the water went through one clarifier bay instead of divided equally between the 4 that I've shown you, then you'd have 3/4 of the plant not doing anything, and your plant would not perform well. And the insight is, the water will not divide equally. There will always be something that makes it not be perfect. And so we're going to be trying to figure out, how do we minimize those imperfections? So here's some places where there are parallel flow. So in the clarifier, in this design, there are 4 clarifier bays. So we want the water to distribute uniformly and flow in parallel through those 4 bays. In each bay, there are something like, how many? Something like 50 or 100, no, 100, something like 100 diffusers that are pointing down into the bottom of the tank. And we would like the same flow out of each of those diffusers. There are plate settlers, and we would like the same flow between going through each plate settler. And if we go to the filter, in this case, we had 2 filters, so we like the flow to divide equally between those 2 filters. There are filter layers. We like it to divide equally between those filter layers. There are branches in the filter layers. We want the flow to divide equally between the branches. And finally, we want it to divide equally between the slots in the branches. So do you see how fine this got? Like, there's so many places where we're assuming that the water is going to just uniformly divide between these multiple paths and everything will be fine. So this is like a review of hydraulics or fluid mechanics. So let's think about, how does this clarifier work? And specifically, why does water move through the clarifier? Where does the energy come from that's pushing the water through these clarifier bays? So let's look at an elevation view of the end of this. So I'm looking at those channels that are dividing the water between the clarifier and, oh, maybe I realize I look at these drawings and I know exactly what's happening because I've been staring at them for 15 years and you've been staring at them for 3 months. So let's just review. Water's coming in this inlet channel, going down through these 5 inlet ports that go to inlet manifolds. It then goes down through the diffusers, around the jet reverser, up through the flock filter, up through the plate settlers, and then into this outlet manifold along the top of the clarifier, out this port, and then it's into this little channel, and that channel has a weir, and it flows over that weir and drops into a channel where it then exits and somehow magically gets to the filters. So the water enters in this channel, and as far as the clarifier is concerned, it's exiting again in the channel that's right next to the clarifier bays. So the question is, what pushes the water from this inlet channel to this outlet channel? So let's look at an elevation view showing what the water levels are. And there's too many things going on, but the blue lines over here point to the water level in the inlet channel. That's the same as the outlet level of the flocculator. Okay, and you also see something interesting, that this inlet channel has a change in elevation. The bottom keeps on coming up as the water goes downstream in that channel. Okay, so that's the water level in that inlet channel. And then over here is the water level in the clarifier bay. So remember, the water goes from this inlet channel, it goes down through an inlet pipe, up through through the diffusers, up through the plate settlers, and ends up at this water level, which is here as well. And then ultimately it goes out through the outlet manifold and goes to this outlet channel. And we see, oh, there's a big change in elevation. Well, big, a small, like 5 centimeter change in elevation between the water level in the clarifier bay and what it is in this outlet channel. So here's my question. Where is the majority of the head loss in the clarifier bay? And this is like a mystery, and I'll guide you through it because it's not trivial. So we have these clues here that are telling us what's going on. And look, if we take the water level that is in the inlet channel and extend that over, we see that the water level inside the clarifier bay is almost exactly, or maybe is exactly the same as the level in the inlet channel. That means that there's almost no head loss, almost no pressure drop, or almost no energy loss between the inlet channel and getting into the top of the clarifier bay. And that's true. And there's a good reason why that's true. And it's related to the fact that, okay, we know, you might remember that plate settlers have almost no head loss. Right? The flow is really slow. The shear on those plates is just tiny, tiny, tiny. The head loss is measured in a few micrometers, which is a ridiculous unit of head loss. So there's no head loss in the plate settlers. But what about the inlet manifold and the diffusers? Why is there no head loss there? Well, what does the inlet manifold and the diffusers, what do they carry? They're carrying flocculated water. And you know that flocks are really wimpy. They're super fragile. And that means that we have to handle them very gently, otherwise we break them. And so if we did have significant head loss in the inlet manifolds or in the diffusers, that would break the flocks, and that's a problem. And so that's why there's almost no measurable head loss. I'd have to go back and look. It's probably order a millimeter, about a millimeter of head loss between the inlet manifold and getting it into the clarifier bay. So that's why that last blue line, that's why that line is horizontal, why there's no significant change in elevation between what's in the inlet channel and what's inside the clarifier bay. So water can get between those 2 points by going through pipes and diffusers and plate settlers, and there's no significant head loss. But then look, there's this big difference in water level between the clarifier bay and the outlet channel. So can anybody figure out where's all that head loss happening? There's a big elevation difference between the water in the clarifier bay and where it comes out of the outlet manifold into the outlet channel. Where did all that energy get lost? Any ideas? Or if you don't have ideas, could you give me a brainstorm of like possibilities, and then we can talk about which one it might be? So this way you can shout out a wrong answer and there's no worries. We're looking for something that would cause head loss between where the water is in the clarifier bay and then it exits by going through these holes. There's little orifices, you can just barely see the outline of it, orifices in the outlet manifold, and then flowing through that outlet manifold and getting to this channel. Where might there be head loss?
When it leaves those little holes, maybe it's because there's a big expansion.
Ah, so that's good. It's going through holes, and then after the holes, there's an expansion, and that is indeed the case. And how would you characterize those holes? Like, if you think back to early in the course, what are those holes? What did we call them? Because we had an equation to describe this. Oh, this is completely unfair. Monroe's asking you questions about like the second week of class. Oof, it was an orifice. And there's head loss for exactly the reason that Dan mentioned. There's a flow expansion. And so the kinetic energy that the water has when it's going through the contraction in the orifice largely gets lost as it's flowing into the pipe. And so we lose energy there. And so that's one place where there could be head loss. The other place that there could be head loss is just like major or minor losses in the pipe itself. There is a minor loss. That pipe does exit into the channel. And so right here, there could be an exit loss. And it turns out that the major and minor losses in that pipe are actually really tiny as well. It's the orifices that are causing the majority of the head loss. And then that raises the question of, well, if we in general, we try to save energy going through the plant because all the elevation drops that we have force us to build a taller building. So it costs us money. So the question is, why is there 5 centimeters of head loss there? So you can hold that as a puzzle. Like, why didn't we just drill bigger orifices? We could have easily done that, right? It would be trivial to make the holes in the pipe bigger. So why did we intentionally make there be 5 centimeters of head loss there? So it is those 5 centimeters of potential energy difference that's pushing the water through the bay and specifically through the outlet orifices. That's how it happens. And just as a reminder of, this is what it looks like when there's water flowing. So this channel has flocculated water. There are the clarifier bays. Here are the effluent manifolds that are dumping water into this outlet channel. And then it's flowing over that weir like a waterfall and into this channel that then is somehow connected to the filters. So what is different about the path of water through the clarifier bays? Does the water have to take, is there any difference in the path that the water has to take to get through these various clarifier bays? Because if there are any differences, that could cause a difference in flow through the different bays. So do you see any difference in the path through these various bays? Yeah, Hannah, what do you see?
They're different sizes.
The bays look like they're different sizes.
Well, I guess not. I guess I was thinking more vertically, like those are different sizes, but like the tubes aren't lined up either, like on either side of the numbers.
Okay, so this is confusing. These tubes, this one is sensor access to flock hopper. So it's just a way to shine a light down there or drop a flashlight in, and that's submersible, and see when you can't see it anymore because it got submerged in the sludge. So that's what that tube is for. And this one is a tube that we no longer use, that was used for allowing us to dump water from the very top of the sediment of the clarifiers. The inlet or the outlet manifolds are placed, in the middle of each clarifier bay. They're identical, but there is a difference in the path that the water has to take to get through the various clarifiers. Because, okay, the flocculator is actually at the bottom of the page off the screen. The water is flowing up in this in this photo. And that means that to get through clarifier 1, it's a shorter path, and to get through clarifiers 5 and 6, it's a much longer path. So the question is, does that cause us a problem? And it potentially does. And I'll come back to eventually how that might cause a difference in flows, because there's a surprising answer to why it causes a difference. It's just another view of the same thing, just to remind you, okay, we can draw this in Onshape, or we can take a picture of the real thing, and they look very, very different. And just this, notice the sloped bottom in the inlet channel, and think about the fact that it costs us money to make that bottom of the channel be sloped. We have to use extra concrete. So that's another thing that we must be doing for a reason. Just to ponder, like, why do we care about that? And here's the stacked rapid sand filter. And again, there's all these multiple paths. And let's think about that for a second. In this case, let's look at these 4 inlet pipes. What fraction of the filter flow goes through each pipe? Or how many layers does each pipe serve? So we can do some quick checking, and look, this top one, it only serves 1 layer, but the second inlet, it serves a layer above and a layer below. And so that's how many layers each of those pipes is serving. And that in itself causes us a problem, because if we use the same size pipes for all of these inlets and outlets, which layers will tend to get the most flow? Well, there's got to be some head loss in the piping system. And so if we have twice as much flow going, or we'd like twice as much flow to be going through the middle pipes compared with the outer pipes are going to end up getting a little bit more water than what we had hoped. They'll get maybe, instead of 1/6 of the water, maybe they'll get, I don't know, 1/5 of the water. They'll get a little bit extra water, and there'll be more water flowing through this bottom layer and this top layer, because it was easier for the water to go through the pipes because there was less flow in those pipes. So that's a problem. So that was all like context. Like, man, there are all these places where there's flow division, and there's differences in the flow paths. So now I have a question for you. And Patrick, I'm going to need a little quiz for that C1 and 2 on there. So how can we make water split equally between several paths in a manifold? So at the bottom here, I've got this blue manifold pipe. You can think of this being an inlet into the bottom of a clarifier, but for some reason it's upside down. I don't know, it's pointed up, but it's a pipe that's sitting inside a tank. I'm not showing what this section, what the left-hand side is connected to. There's an elbow there, and it's going up and it's connected to something, okay? But so we're dumping water into this tank. And you should think of my entire PowerPoint slide as being underwater, okay? And I'm gonna be dumping water, forcing water into this pipe. And I'd like the ports 1 through N, to each have the same flow. And to make it easy to fabricate, I want all of those ports, the orifices, and I want their diameters to all be exactly the same. But my question to you is, well, okay, I'd like QP1 over QPN, the flow out of port 1 divided by the flow out of port N, to equal 1. That's what I'd like to have happen. There's a reason why I'll never get that, but I'd like you to think about, what could I do to get closer to having that ratio equal 1, meaning I get uniform flow? So should I increase the diameter of the orifices to make the flow more equal between ports? Or should I decrease the diameter of the orifices to make the flow more equal? Let's vote. Patrick is on to me. Okay, I'm curious what you come up with. Well, it means that almost 30% of you no longer trust Monroe, which is good. That means that you're skeptical, and I want you to be skeptical. So that's very, very good. 20% say you should increase the diameter, and 50% say you should decrease the diameter. And those 50% scored. Those 50% got it right. You should decrease the diameter. And I will try to explain why that matters and why that makes sense. And to understand why decreasing the diameter helps, we have to first understand the source of the problem. Like, why is it that the flow isn't uniform between these ports? And if we can understand why the flow isn't uniform, we'll then be able to understand why decreasing the diameter of the ports actually helps. So here are 4 strategies that we could try to solve this problem of getting equal flow. We could make all the paths identical. So if you have a way that you can make all the paths identical, that's an interesting option, because that completely solves this problem. If the paths are identical, you have no problem. You could add custom head loss to each path. That's complicated. You could increase the identical head loss in all paths to make the differences insignificant. I wanted to read that like 3 times. But if there is some unintended difference in head loss in the different paths, if you make the head loss in all of the paths intentionally larger, that could dominate the small difference that's there. And we actually use that technique. You could reduce the head loss. You could use a large diameter pipe for the manifold. And let's go to why. So some physics. And we're going to do an aside first, which is just because it's fun. It's fun for me, at least, because I get to ask you another question that is troubling. And by the way, the stuff that we're talking about today is not something that is just easily intuitive. So how do you know which way water will flow in a pipe? And by this all connects in the end, okay? So here's 2 hypotheses that you, I'm sure, have heard. Water flows downhill, so goes from higher elevation to lower elevation. Or you might have heard that water flows from high pressure to low pressure. Yes? You've heard one of those or both of those? Huh. Well, I'm going to prove that they're wrong. So let's take a swimming pool and let's drop a pipe into the swimming pool. All right. Now take your favorite explanation for which way water flows in a pipe. If you believe that water flows from high elevation to low elevation, then it's going to flow in that direction. And if you believe that water flows from high pressure to low pressure, pressure goes down as you go down in the pool. So if we go from high pressure to low pressure, that means it's going to flow up. And what do you know is actually happening? If I drop a pipe in a pool, does water flow in the pipe? Good. You all know that perpetual motion is not a thing. If that ever changes, we're suddenly rich, right? Because we install a turbine, we generate electricity, and we solve the world's energy problems. But in the meantime, it means that the rule of water flows from high pressure to low pressure, or water flows from high elevation to low elevation, isn't simple enough. Those are too simple. We need a better explanation. So the actual explanation is water flows from high piezometric head to low piezometric head. And so let's try that. So I will make the case in the next slide. I'm going to use a new symbol, PSI, and I'm going to stumble over it, psi, that is the sum of the pressure divided by rho g plus the elevation. So here's another fun thing. Now we've added a sloped pipe, that same slope pipe we had before, but we've connected to another tank up above, and we have our swimming pool. And the first thing we want to do is we want to figure out what the piezometric head is at 0.1. So let's try it. So we have piezometric head is pressure divided by rho g plus z. If we defined z equals 0 at the water surface of this tank, which is just a really convenient datum, and if we say that the pressure, that atmospheric pressure is also our datum, then we can say that the pressure at the surface of the tank is 0. And now, what happens? As we come down, P1 is equal to negative rho g times z1. And because pressure equals rho gh, and that height difference is negative z1. So that means that piezometric head is 0. Piezometric head in a lake is 0, which all that means is that if you take a straw out to, let's see, you're not that close to Lake Ontario, but no, it's Erie, which is above you. It's Erie. Okay, if you would go up to Lake Erie and stick a straw into it, how high would the water rise in the straw? The water would rise to the surface of the lake. And that defines your datum of if your z equals 0 point is the surface of your lake, that's a representation that piezometric head is 0. If you want to go into real detail, you would have to think extra hard about what happens when you have density differences inside the lake. So for right now, we're ignoring that just to make our lives easy, okay? We assume a lake full of water that's all the same temperature like it is right about now. Okay, so the piezometric head is 0 everywhere in the lake, which means that there's nothing moving the water around except the wind that's pushing it on the surface, but there's no pressure or piezometric head differences driving water flow in the lake. And if we go inside this pipe that I have closed off, but it has water at a higher level, what is the piezometric head there? So its water surface is h higher than the lake's, and so its piezometric head is actually equal to h. So the piezometric head inside this pipe is h, and the piezometric head in the swimming pool is 0. And that means that if I drill a hole anywhere along this manifold, this pipe, water will come out because water goes from high piezometric head to low piezometric head. Am I convincing you? So piezometric head at 2 is h. And if I now put orifices in the side of that tube, water will flow out of all those orifices. And the reason it flows out is because there's this piezometric head difference, and it all looks great. So what sets h? Oh, what sets h? Can you think about that? What is determining h in this? Like, what determines how deep the water is in that tank, in the upper tank? That pressure is, can you tell what would happen if I increase the rate of droplets going into this tank? What happens? Like right now, I just have a droplet a second going in. What if I increase the rate of droplets going in? What's going to happen to h? Okay, it's gonna spill over because I didn't have the tank at h drawn any taller. But if I increase the flow, h has got to increase. What's causing all that head loss? What's causing h? It's the head loss going through the pipe and coming out the orifices. So H is set by the flow rate and by the head loss through those orifices. Okay, let's write the energy equation. So there's our friend, the energy equation. The piezometric head is the pressure and the elevation difference, or the elevations. So there's a piezometric head on each side of the energy equation. And we can look at what's causing a difference in the piezometric head. So now we're going one layer deeper. We're realizing, oh, maybe there's another reason why the piezometric head changes inside a pipe. And it turns out, unfortunately, that there is a reason why the piezometric head changes, because look, if we put a control surface at 1 and a control surface at n, the velocity in the manifold pipe is different at those two control surfaces. Up here at 1, there's a lot more water flowing through cross control surface 1 than there is to control surface n. That means V1 is a whole lot higher. And that means that there is a change in piezometric head related to two things, either caused by the change in velocity in that manifold pipe, or due to head loss in the manifold pipe. And in a water treatment plant, our pipes are relatively short often. These manifolds are often relatively short, and so head loss ends up being pretty insignificant. And that means there's a change in piezometric head in a manifold because the water is moving and it's changing velocity. And where's piezometric head higher? This is where the surprise pops out. Where is piezometric head highest in that pipe? VM1 is a big number. VMN is a small number. So that means that delta piezometric head is a positive number, which means that piezometric head is actually increasing in the direction of flow. The piezometric head actually gets larger as you go down the pipe, because the water inside the pipe is slowing down, and as it's slowing down, some of its kinetic energy is turning into potential energy. This is like the crazy big surprise of manifolds. So did you see what happens? Because water in the pipe is slowing down as it goes down the manifold, the piezometric head is actually increasing. And that means that the last port gets more flow coming out of it than the first port. And I can just about guarantee that if I had given you a question on that one, you would have said that the first port gets the most flow because that's the shortest path. But for the case where head loss in the major losses in the manifold pipe, for the case where that is insignificant, it's the last port that gets the highest flow rate. And I love the fact that I see some puzzled faces, because you're like, that can't be right, Monroe. You've got to be pulling our leg. And I'm telling you, I'm as serious as I can be. I'm not pulling your leg. This is actually the way the physics works. If there's significant head loss, that changes the equation. Because remember, I dropped head loss off the equation here. But there often isn't significant head loss in these pipes. So the change in piezometric head is due to this change in kinetic energy. It's about the kinetic energy term in the energy equation, and the fact that there's a change in kinetic energy and it's being converted into potential energy. because the flow expansion that's effectively happening inside the manifold is happening very, very slowly, it's actually pretty efficient at converting that kinetic energy into potential energy. Remember, if you do a sudden expansion, you lose almost all the kinetic energy. But here we're doing a very gradual expansion as the water is going down this manifold. And the result is that we recover that kinetic energy, turn it into increased potential energy, and the last port gets the highest flow rate. So I want to just show one other place. Oh, let's do this. No, I already told you the answer to this question. The last port has the highest flow rate. So you're going to get it right now, right? The last port has the highest flow rate. And now can you think about why, okay, it's the kinetic energy change in the manifold that's causing us problems. How could you change the design of a manifold so that there's not as much change in kinetic energy in the manifold? Which is the same as asking, how do you reduce the velocity in the manifold? Because if I reduce the velocity, I'm reducing how much kinetic energy there is. So how do I reduce the velocity in a manifold? I make it bigger. So you could solve the problem by making a monstrous manifold. That's one very viable option. And it's one that we always have to play with. And there's always this economic trade-off. The other approach is, what if instead I make really tiny orifices? Now I've got lots of head loss through each orifice. And that means that the difference in the pressure, so now the pressure inside the manifold, or the piezometric head inside the manifold, is going to increase a lot. I'm going to have more total piezometric head. So my average piezometric head, my psi m, my average piezometric head is going to be much larger. And the delta piezometric head, assuming I'm keeping the same size manifold, is still the same. But it means that the difference in piezometric head doesn't matter so much because it's a much larger total. Let me say that again. The difference in piezometric head between inside the manifold and outside the manifold is really big. The difference in piezometric head inside the manifold is tiny. And so that tiny change doesn't matter so much. So we can make the change in piezometric head inside the manifold not be significant by making there be a huge difference between the piezometric head inside the manifold and outside of the manifold. And we can do that by using teeny tiny orifices. So the other solution is just drill the tiniest holes you can make inside this manifold from one end to the other, have the water shooting out of there at 1 kilometer per second, and there will be no difference in flow between those various orifices because the difference in piezometric head inside the manifold is inconsequential. Also, did you see that no matter what we do, we pay for it? We either pay for getting uniform flow by building a big manifold or by using more energy. Sorry, we have to do one of those. And it's always going to be a trade-off there. I want to just end with just to show another illustration of where this shows up in the design. And aren't you glad I'm not showing you all these equations? But the equations are there if you want to actually know the math for how do you actually figure out how big a manifold needs to be, okay? But here's another place in the plant where it's a slightly different system, but we have a different kind of a manifold. It's a channel. So the channel that's delivering water to the filters, the water might be flowing in through this end here, and then it's being delivered to both of these filters, and it's flowing across a weir. And now, which filter gets more water? I should have numbered them, but is it the filter that's closest to you or the filter that's further away from you, given that the water is entering from the side that's closest to you? Which filter gets the highest flow rate?
It's got to be the closer one.
See, intuition sucks.
Yeah, because then you talked about how the last one gets the highest flow though. So now I'm like, I don't know.
Yeah, so see, intuition tells you that it should be the closest path. The shortest path should get the most flow, but it's wrong. I'm sorry, it's wrong. It's the last filter that gets the most, because the water that's flowing in this channel literally piles up at the end of the channel and pushes more water over the weir. The water has more velocity entering the channel. Here's another way to think about it. In order for the water in the channel to slow down, somebody's got to push on it and make it stop. And that somebody is the end wall. The end wall is pushing on the channel. And in order to push on it, the water actually builds up a little bit right at the end of the channel. And so the water level is higher at the end of the channel. The last filter gets the highest flow rate. And so we have to make the channel big so that the velocity in the channel is low. And we have to have a fair amount of head loss over these two weirs so that the change in water depth in the channel doesn't matter. Wow, with that, now that you've been shocked in realizing that the shortest path is not necessarily the way the water will choose to go, I will quit. I do want to share one cool thing with you guys, and that is that we have been working on creating a new chapter in the textbook that has links to all of our toys, all of our design, our smart parts. And so I'm putting this in the chat. And I know that you are overwhelmed at the end of the semester, but if you need a diversion where this doesn't cost you anything, Monroe's not going to give you any quiz on this, but if you want to play with all of these smart parts, there they are. There's a chapter with links to all of the smart parts. Each of those smart parts, you can play with the configuration. And what I would ask in return, you knew there was nothing for free, right? There's a survey on there, and this is optional. But if you get a chance to play, and if you have any feedback, like, I need to understand, give us more information about how to use this, or you have an idea of something that we could offer to people that might be playing with us, or something that they could do to learn more about it, we would welcome suggestions. This is not yet really released to the public. It's kind of hiding in the textbook in a place that nobody will find it unless I tell them where it's at. But we will eventually release this to the public. And so I'm looking for suggestions on how to make it interesting for people like you to play with it. Okay. And with that, I'm done, and I'm ready to go hop over into Gather and